Welcome to the second video in Unit 4, where we're discussing the structure and reactivity of carbonyls. In the last video, we talked about this concept that carbonyl carbons are electrophilic and carbonyl oxygens are nucleophilic and basic. And it doesn't necessarily matter what's attached to the carbonyl. Those roles are essentially always going to be true. But what we also alluded to at the end of that video is that these substituents, or the R groups, these are going to control how reactive the carbon and oxygen of carbonyl is. So I want to be very clear about this language. How reactive means the substituent is controlling essentially the volume knob. It's not controlling the power switch. So like all carbonyl carbons are electrophilic. The question is to what extent? And the substituents are what we can analyze to decide to what extent, especially if we're making comparisons between carbonyl containing functional groups. So for instance, if we were thinking about a ketone versus an acid chloride, maybe we could look at the structures of a ketone and an acid chloride and make some qualitative decisions about which of those two carbonyl oxygens is more basic, or which of those two carbonyl carbons is more electrophilic, right? So in this video, our goal is going to be to develop a framework so that we can do this kind of analysis. I want to be clear again, the point is not for you to memorize the results that we develop in this video. It's for you to understand how we came to those results, because you will be evaluated either on homework and or an exam with substituents we haven't talked about in this video, and you'll have to use the framework that we're developing here to do the analysis for yourself. So let's get started. We're going to focus first on carbon electrophilicity. So we will do both analyses for carbon electrophilicity and oxygen nucleophilicity and basicity. What we will eventually find is that they are related to each other. But it'll be much easier for us to have this conversation by just focusing on one role and one atom, this carbonyl electrophilicity. We'll start by establishing what makes something more or less electrophilic, excuse me. So electrophilicity is going to increase as the electron density of the atom that we're maybe saying is the electrophilic site decreases. So another way of saying that is that as an atom becomes more positively charged, or at least partially positively charged, that atom will tend to become more electrophilic. Alongside our discussion of electron density, we also need to be cognizant that when a nucleophile and an electrophile react, not only are they going to be attracted by differing charges, where the electrophile is going to tend to be partially positively charged and the nucleophile will be partially negatively charged, those two pieces actually have to be able to touch each other or get close enough to each other for the bond to actually form. So we also know that electrophilicity is going to depend to some extent on sterics. So we can also say that electrophilicity goes up as steric hindrance goes down. What we mean by that is that the groups that are nearby the carbonyl will tend to be smaller in better electrophiles. If I had to choose one of these two features that's going to drive reactivity differences, I would focus mostly on electron density. Sterics and how they influence reactivity are a little bit like going bankrupt. So these things matter a little bit, and then they matter all at once. So like structures with butyl groups or the really large groups, their reactivity can be dominated by steric hindrance. But in a lot of other cases, it's usually sufficient to actually look mostly at electron density and get some pretty good ideas for relative reactivity. But we will see some cases where we invoke this concept of sterics in our framework as we develop it. The next thing we need to establish, now that we've decided we're focusing on electrophilicity of the carbonyl carbon, is if we're going to do these structural analyses, we'd like to be able to check them using data, using some kind of experimental result. So how do we measure electrophilicity? There are lots of ways we could potentially do this. Probably the crudest way to do this is to react a set of carbonyl containing compounds with like a reference nucleophile. So we would have a variable, which is the structure of the carbonyl containing electrophile, and we would react each of them individually with the same nucleophile. And what we could do in that situation in a very general sense is measure how long the reaction takes. So a slower reaction would correspond with lower electrophilicity. Basically what we're saying is that we're going to have to wait longer for the reaction to happen because the carbonyl that we're actually looking at in that particular reaction isn't very good at its role of being an electrophile. So it's going to take it longer to do it. So we'll measure reaction time, but we're going to measure a specific kind of reaction time because, again, we want to compare across cases. The easiest thing for us to do in this situation is actually to measure half-lives. Which we'll remember as T1 half. So basically what we're going to do is run a reaction with a carbonyl containing molecule, maybe a ketone for instance, with our reference nucleophile, whatever that's going to be. And we'll see how long it takes for exactly 1/2 of the carbonyl containing molecule to disappear, turn into the product. That's the half-life. We should be able to compare half-lives and correlate those with electrophilicity of carbonyl carbons. So as our half-life goes up, that means it took longer for the reaction to get halfway to completion. That means that our indicates, important word, indicates the electrophilicity is going down. So essentially as the reaction starts to take longer, we're working with worse electrophiles. So in the next section of this video, we'll be talking about some specifics with how this experiment would actually be designed. We'll talk about what the reference nucleophile is, for instance. And then we'll also start to look at comparisons. So we'll look at the actual half-lives for two different carbonyl compounds, and we'll start learning what kinds of structural features impact electrophilicity from these vignettes or individual comparisons. Let's first talk a little bit about the experiment that we'll be performing to measure our half-lives so we can actually make some experimentally determined conclusions about what kinds of structural features influence carbonyl reactivity. So we would pick our carbonyl compound. I've left it generic because remember that our R groups are essentially going to be our variables in this experiment. And we're actually going to react the carbonyl with an excess of water. So the oxygen of water we know is nucleophilic because it has lone pairs. That was all that was required for an atom to be basic, and it's all that's going to be required for an atom to be nucleophilic, for instance. I've written product because it's going to depend on what the R groups are, and it depends also on whether the compound is a carboxylic acid derivative or a ketone type structure, what the product would actually look like. We'll talk about that in more detail in Unit 5 of this class. So once we do this reaction, what we're going to be doing is measuring the concentration of the carbonyl compound. And once that concentration drops to half of what it was when we started the reaction, that's the half-life. So we would typically do this with either NMR. We could use carbon-13 NMR to get a very clear signal of the carbonyl. We would have to do the experiment in such a way where integration mattered. This was a common misconception that came up in homework 1 and the discussion board. Carbon-13 NMR, typically we don't actually integrate the peaks for kind of technical reasons, but it's possible to do carbon NMR experimentation where you can get good reliable integration values. This is not typical. The other thing we could do is use IR. We could actually look for the extent to which the signal that comes from the carbonyl disappears, and we could actually quantitate that using a strategy not dissimilar from how you might have interacted with Beer's law in general chemistry lab. So again, I'm not going to evaluate you on those techniques. I just want you to know, just a little bit like NMR, that these are not like black box ideas that are coming out of nowhere. They come from experiments that you could really understand. So all the data that we see in this video will be from the same set of experimental setups. All that will really be changing is the nature of the R groups in terms of structure, right? We choose an excess of water here so that the amount of nucleophile makes no difference. In all experiments, it's essentially a wash, if you will, and the only thing that's really dictating our half-life is our independent variable, the structure of the carbonyl itself, or the substituents on that compound. Let's look at our first comparison case. We'll look at what's called a primary amide. Primary because the nitrogen is attached to one non-hydrogen substituent. So it's a little bit like a primary alcohol, except for here we're counting the number of non-H groups on nitrogen rather than adjacent to the oxygen. We've also got an ester, so these are the two structures that we'll be comparing. And the idea is that we should be able to measure half-lives for the amide reacting with water and the ester reacting with water, and that will actually end up telling me, of these two carbonyls, an ester carbonyl or a primary amide carbonyl, which one is more electrophilic. So here's the actual data. Our half-lives here. Our ester is about 2 years. So this is extrapolated. We probably didn't actually measure the half-life. We probably measured the 0.95 life or something like that, and then we're able to extrapolate out to what the half-life would be. The primary amide is around 4,000 years. So, a little different. Again, we're not, no, there's not some immortal scientist that's measuring this value, it's extrapolated. But these are pretty reliable differences. Clearly the ester is far more reactive than the amide. Now what's left for us to do is to come up with an explanation for why that is. So let's do that together. Whatever explanation we choose is going to have to match our underlying understanding of chemical reactivity. And since we're assessing electrophilicity, like we talked about in the previous section of the video, we're going to try to explain why the ester apparently has a more electron positive carbonyl carbon than does the amide. So carbonyl C is more partially positive. Remember we talked about the concept of sterics as well. There aren't large differences in sterics between these two structures. So given the yawning gap of half-lives here, probably whatever's happening we could attribute to electron density arguments. But how are we to know that the ester carbonyl carbon is more delta plus than the carbonyl carbon of the amide? Well, we can use tools that we actually developed in our discussion of acid-base chemistry. Remember back then we were talking about how we would stabilize buildup of charge or buildup of electron density in conjugate bases, and we invoked methods of essentially moving electron density around a molecule. The same thing would apply here. Here we're talking about moving electron density away from the carbonyl carbon or toward it. Either of those could modulate this notion that we're developing a partial positive charge. So specifically, our explanation is going to involve things like induction. Let's apply this concept of induction to our ester and our amide, and we're going to focus specifically on the functional group, or the substituent rather, excuse me, that's actually changing here. So if we were looking at the primary amide, it would be the nitrogen and the things attached to the nitrogen, and we would compare that to the oxygen and the things attached to the oxygen in the ester. Another way we could talk about that is by drawing a box around the substituents that are going to be driving differences in reactivity for these two structures. So, well, for induction, well, we're going to consider our dipoles, like this bond polarization, and specifically the polarization between the oxygen, or whatever is in the box that's connected to the carbonyl carbon. So I know that this bond is polarized away from the carbon and toward the oxygen. Another way of saying that is that our substituent here is an inductive acceptor. We could also look at the amide and do the same assessment where we're going to compare electronegativities of carbon and nitrogen, and that's going to tell us that the bond between our carbonyl carbon and the nitrogen here of the amide, it's polarized also. So that means the NH2 group is an inductive acceptor. Okay, so crap. I've got two inductive acceptors. How am I going to explain differences in that way? We'll make sure we take some notes. Both substituents are inductive acceptors. Oh, and by the way, I know it's probably boring to watch me write on the board for this. maybe more than anything else this semester, it's really critical that you write down what you're deciding as you're doing it when you do these analyses, because as we'll see by the end of this video, a lot of times you have many, many decisions to make about a single binary comparison for two structures. And it's going to be very difficult to keep everything in your head straight if you don't write anything down until you figure the problem out. So both of our substituents are inductive acceptors. We also know that there's a difference in electronegativity between nitrogen and oxygen. And that might help us. So I guess what I want you to decide is which of these two groups, NH2 or the methoxy group, is a stronger inductive acceptor. One of the things that you might have thought about is that nitrogen is less electronegative than oxygen. And that means that this dipole between carbon and oxygen will be larger than the dipole between carbon and nitrogen. We could exaggerate that graphically. We remove our dipole, for instance, and use partial charges instead. We could write like a big plus and a big minus because there's a lot of polarization, a big difference in electronegativities here. On the other hand, for our carbon-nitrogen bond's polar, but because nitrogen is less electronegative than oxygen, this difference will be smaller. So I've got like delta plus, delta minus. So yes, both groups are inductive acceptors, but the oxygen group is a better or a stronger inductive acceptor. And just to remind us how we decided about this relative strength of inductive acceptors, we compared the electronegativity of nitrogen versus the electronegativity of oxygen. So here, when we're saying that this group is a stronger inductive acceptor, we're saying that the ester is more electrophilic than the amide because the oxygen of the ester, the thing that makes it an ester, not some other kind of carbonyl, is pulling more electron density away from the carbonyl carbon than the nitrogen could from the amide. Okay, well that seems to make sense. We want to evaluate this hypothesis. This is like a hypothesis now. It came from some exploratory data. Let's pick another compound to bring into this comparison set that would allow us to evaluate that. So maybe we would want to pick something that like had a substituent like in the box that would be either like maybe not an inductive acceptor at all, or was an even more powerful inductive acceptor than the ester. Either of those would be possible, and that would help us to know, like, is this a general result? Can I use this concept across all kinds of carbonyl structures? Or is it only applicable to esters versus primary amides, which would be like less awesome. So the next section of this video, we'll do exactly that. I'm going to clean up the board a bit, redraw my structures, and we'll bring in our third comparison structure here. Let's compare our amide and our ester to a ketone. Or in other words, what we're going to do is compare a methyl group as a substituent to an NH2 to a methoxy group. So I've done a few things. I've cleaned up the board like I said I would. I've also moved the half-lives above the structures. So you can see your primary amide, 4,000 years. For ester is about 2 years. I have yet to give you the half-life for the ketone. But first I want you to actually use the hypothesis to make a prediction. So here our hypothesis is still written here. I want you to predict the relative half-life of the ketone in our reaction relative to the amide and the ester. Or in other words, like, is this half-life going to be between these? Is it going to be less than 2 or more than 4,000? So make your prediction and then start your video again. If we apply this hypothesis that relative inductive accepting is going to correlate with electrophilicity, then it would seem that this methyl group is really like not an inductive acceptor at all. The carbon-carbon bond is not really polar in any meaningful way, right? And that's certainly not relative to like a carbon-nitrogen or a carbon-oxygen bond. So not an inductive acceptor. And if that's true, then I should expect the carbonyl carbon of a ketone to actually be even less electrophilic than an amide, right? So here would be the strongest inductive accepting and therefore the most electron poor carbonyl carbon. That would have to be the fastest reaction, right? So basically what we're saying is that the half-life of the ketone should be more than 4,000 years. if this hypothesis is correct. If it's not correct, then who knows what the value will be. Well, here's the data, 21 hours. So not only is it different in numbers, it's different in units. All right, this is going to be reaching halfway to completion in basically a day, let's say, 4,000 years. So how do we do? Well, I'm confident that this is true. I know this from structure. I know I can assess bond dipoles. I didn't do anything wrong there. But this didn't work, right? The prediction that I made, or that maybe we all made, on the basis of this alone, clearly failed. It's not enough just to analyze induction. We have to be very careful to think about how substituents can influence carbonyls by way of conjugation or resonance as well. So let's look at our amide and our ester. In this case of the ester, I see that the oxygen actually has a lone pair that can be donated toward the carbonyl carbon. And that's going to make the carbonyl carbon more electron rich. So we could say that, I'll draw the resonance structure for completeness sake here. Oops. There we go. So we could say that this oxygen group here is an inductive acceptor, but a resonance donor. So that's kind of complex. The substituent is doing two things at the same time. It's removing electron, well, let me line myself up here. It's removing electron density from the carbonyl carbon by way of induction, while at the same time putting it back into the carbon by resonance. And as we established in acid-base chemistry, oftentimes this resonance effect is going to be more powerful than any kind of inductive effect. Well, let's see if that's actually true here. So let's assess our nitrogen now for the same concept, right? It's the NH2 group is, as we established, definitely an inductive acceptor. But just like the oxygen and the ester, it looks like the lone pair of nitrogen can be donated by resonance toward the carbonyl carbon. So I would have a resonance structure here. So it looks like the nitrogen is also a resonance donor. And then finally, we can look at our methyl group, or CH3 group. We decided that there's not really any bond polarization here, so the methyl group is not really an inductive acceptor. And can this carbon donate electrons toward the carbon of the carbonyl by resonance? No. This carbon doesn't have any pi bonds, it doesn't have any lone pairs, and it doesn't have any p orbitals, and therefore it can't actually participate in this kind of conjugation. So no inductive effect and no resonance effect. All right, so what we're seeing here is that losing the resonance effect, or at least losing the resonance donation, actually makes the carbonyl carbon really reactive, quite electrophilic, relative to cases where you have substituents that are resonance donors. The other thing that we can conclude from this example is that even if you have inductive acceptors, right, the resonance effect overpowers the inductive effect. Let's do a little thought experiment, right? If induction was a lot more important than resonance, shouldn't the amide be more electrophilic than the ketone? But we actually see the opposite, right? So we can take from this comparison of three compounds a couple of really important takeaways, things that we want to use for the rest of the semester. So we should write down some of these conclusions that we're making now. The first is that we always must assess resonance and induction. It's never sufficient to look at one or the other. It may be the case that a substituent only has one effect or the other, but we need to make sure that we've done the assessment to know that. So we need to, every time we think about reactivity, frankly, of any atom, for any purpose, the same thing was relevant for acid-base chemistry, right? We need to make sure we take both of these features into account. And the other is that we're seeing more experimental data to support this kind of razor, this kind of simplifying assumption that all else being equal, resonance is going to be more significant or a bigger driver of reactivity than induction. Both of these are really critical ideas, because if we're always going to be assessing both resonance and induction, it turns out that a lot of times they fight each other, like we're seeing in the amide or the ester. So we would need to know, like, which of those two effects should we privilege? Should we say is more important than the other one, since they are fighting each other? And my argument is essentially that in most cases, not all, but in most cases, we can just assume that these resonance effects are going to dominate over whatever induction is doing. So that means that I can describe the NH2 group, for instance, as a net donor. I'm accounting for the fact that the NH2 group exerts its influence on the carbonyl carbon through two different means, both induction and resonance at the same time. It might help to actually put some kind of hypothetical numbers on this. These aren't real, but they serve a purpose for seeing what we mean by net donation. Imagine that the NH2 group, it's removing 10 electron density points by induction. So that's like minus 10. And it's donating 100 electron density points by resonance. Remember that we're saying resonance is more important, thus the 100 is greater than 10. That means that overall, the nitrogen is donating 90 electron density points. It took some away, it put a whole bunch more back, and after everything has been taken into account, it's actually donating overall. The same thing is true for the ester, right? We actually see that there's inductive donation and inductive accepting and resonance donation. So the methoxy group is also a net donor, but this difference in half-lives, where the ester is a lot more reactive, reacts more quickly, it tells me that the methoxy group relative to the NH2 is a weaker donor. Maybe we could describe that in another way. We already established that this oxygen is a better inductive acceptor than the nitrogen. So in our silly numbers analogy, maybe the methoxy group subtracts 30 electron density points by inductive accepting. Maybe it donates 100 electron density points by resonance, although what we'll find in the next video is that not all resonance donation is equal. And that gets us to donation, but less so than the amide case. And that would square with what we're seeing with with the half-lives, excuse me. So finally, we can come to our ketone and describe, well, what's the methyl group doing? We don't really have an inductive effect to speak of, and we decided we have no resonance effect. The methyl group strictly does not interact with the carbonyl by resonance. So this is a net nothing, more or less, right, to a first approximation. As we will see in the next video, alkyl groups like methyls do actually influence carbonyls, but by a mechanism that might be a little bit different from what we've talked about so far. So to recap, we've established two really critical ideas that's going to be relevant for carbonyl chemistry all throughout the semester, but I would argue is true for organic chemistry, period, and for anything biochemistry where there's structure involved. And that's that resonance and induction happen at the same time. We need to assess them both, and in cases where they compete with each other, in the absence of any data to support ignoring the rule, resonance is going to be more important than induction. So that concludes this video. We've done a lot. This is kind of the heart of the unit, what you saw in this video, and it's something that a lot of students struggle with. So I would encourage you to work some practice problems once you've watched this video, as well as the next one, before you actually try to tackle the homework, right? So that you'll get good feedback from working SLO problems, then checking your solutions, before you really dive in and try to do some homework where points are on the line.